Hello students, I am Sushmita J, Faculty, Department of Computer Science and Engineering, Acharya College. I believe everybody is safe and doing good at your home. In concern with your SS and OS lab, in the curriculum we have 9 programs in which 3 was your Lex India, 3 programs on operating system and 3 programs on compiler design. 3 programs on Lex India was completed when we were in college. Now the next 3 programs on operating system shall be taken one by one, and followed by that would be your programs on compiler design. So the very first program on your operating system, that is your experiment number 7, it is a program on the concept of your scheduling algorithm. There are various scheduling algorithms available, but the experiment tells the implementation of 2 scheduling algorithms, that is your shortest remaining time and round robin. So we will take a detailed look of what your shortest remaining time and round robin scheduling algorithm is all about. That would help you in designing a program. So before I get into the scheduling algorithm, we shall look into what is the broad category of your scheduling algorithm that is there. There is 2 broad category of scheduling algorithm, that is non-preemptive and preemptive scheduling algorithm. So when do we say it is non-preemptive and when do we say it is preemptive? That is done based on the following 4 conditions, which is also a concept part of your operating system regular curriculum. So whenever a process is switching from running state to waiting state, or when the process terminates, we say it is a non-preemptive scheduling. When the process switches from running state to ready state, or when the process switches from waiting state to ready state, it would be a preemptive scheduling. To simplify it even more, I call a scheduling algorithm non-preemptive when a process is allocated to the CPU and this process voluntarily gives up on the CPU. It is a non-preemptive scheduling. Whereas in your preemptive scheduling, when a process is allocated CPU and the process is forcefully removed from the CPU and another process is allocated, that is a scenario where we call it a preemptive scheduling. So as your experiment tells, it tells you the implementation of your shortest remaining time and round robin. And in that, what is that we are going to look for? There are many scheduling criteria available, but mainly we look for the calculation of your waiting time and turnaround time. So the definitions of your turnaround time and waiting time is as follows. The turnaround time is the amount of time to execute a particular process. Waiting time is the amount of time a process is being waiting in the ready queue. Now how do we calculate these two in different algorithms is what we will be discussing further. Now talking about scheduling algorithms, as I told it to you earlier also, there are various scheduling algorithms that is available as seen here, and you will be studying all this scheduling algorithm as a part of your theory curriculum in your operating system. But what is the requirement here for your experiment? We will only be implementing 2 of it, that is your shortest remaining time and your round robin. Now what are the features of your shortest remaining time? What are the features of your round robin? How do I calculate the average waiting time in round robin? How do I calculate the average waiting time in shortest remaining time scheduling is what we will address to. For the sake of convenience and for you to understand how the algorithm works, I have taken the first come first serve scheduling as well. This is a very basic and a easy scheduling algorithm that is available. So to show you how the calculations happen, for the sake of explanation and example, I have considered this scheduling algorithm as well. So what is your first come first serve scheduling algorithm? The process that requests the CPU first shall be given the CPU immediately. So in the order in which it arrives will be the same order in which the CPU shall be allocated. So what do we do with that? This is a snapshot of the process with its burst time. Say I have three process P1, P2, P3 with the following burst time. That is, process P1 has a burst time of 24, process P2 has a burst time of 3, and process P3 has a burst time of 3. So we design a Gantt chart like this, showing which process is executed in which order. Now what is the algorithm demanding? We need to calculate the average waiting time and turnaround time. Now how do I calculate this average waiting time? You can see there in the Gantt chart, process P1 is not waiting at all. It is the first process that is asking for the CPU and it is immediately granted. So the waiting time of process P1 is 0. Now process P2 have to wait for 24 milliseconds. So after 24 milliseconds, process P2 is allocated the CPU. So the waiting time of process P2 is 24. Similarly, for process P3, the waiting time is 27. After 27 milliseconds is where P3 gets a chance for the CPU. So we will be taking the average waiting time as shown here. So this is for your first come first serve. Now what is it with your shortest and how, I just missed out the turnaround time, so let me take up that as well. So how do I calculate the average turnaround time? So as the definition tells, when it is completed the process. So P1 is completed at 24, P2 is completed and given up the CPU at 27 milliseconds, P3 is completed and given up the CPU at 30 milliseconds. So the average of these three gives us the average turnaround time. This is a method of calculating your average waiting time and average turnaround time. Now how do we do the same thing with your shortest job first? Shortest job first is a scheduling technique in which the process that has the shortest burst time will be the first to be given the CPU. In the previous algorithm, we only considered the arrival. Whichever process came first was the first process the CPU was allocated. But in this case, we are considering a process that has a smaller burst time. So whichever has the smaller burst time will be the one which is going to get the CPU. Now in this again we have both the versions. We have non-preemptive version and the preemptive version. So what happens in the non-preemptive version and what happens in the preemptive version? In the non-preemptive version, we see all the process, we see whichever is the shortest, we sort all the process by the burst time. Whichever process has the shortest burst time, we execute in the order from small to large. Okay, now what happens in the preemptive version has the definition we have seen earlier of preemptive and non-preemptive scheduling, where the process is forcefully taken out from the CPU and given to another process. The same holds good here. If a process arrives with a lesser time, so the process that is executing on the CPU shall be preempted and the process with a lesser burst time shall be assigned the CPU. This is also called as shortest remaining time first scheduling. This is the scheduling algorithm that you are expected to implement. Now let us take an example to see how this is actually happening. So taking the snapshot of the same, so you have a process, you have 4 processes with burst times, process P1, P2, P3, P4 with the burst time 6, 8, 7 and 3 respectively. So now if it is a non-preemptive version, what happens, as I said earlier, it shall be sorted in the order small to large, and you will be giving to the CPU in the order small to large. Whichever has the shortest burst time will be the first to be executed. Now among the 4 processes, I have P4 with the shortest burst time. After P4 it is P1, after P1 it is P3, and after that it is P2. You can see the Gantt chart that is represented in the same order. So I will be giving my P4 first, then P1, P3 and P2. Now the waiting time has similarly calculated for the first come first serve. So P1 is waited for 3 milliseconds, P2 has waited for 16 milliseconds, P3 has waited for 9 milliseconds, P4 happening to be the first process to be given, so it has not at all waited, so it happens to be a 0, and you will be calculating your average waiting time. And turnaround time is the same with the process when it completes the execution. So P1 completes it at 9, P2 completes it at 24, P3 completes it at 16, P4 completes it at 3. So you will eventually be calculating your average turnaround time by summating and taking the average of this. The next thing that we have is the preemptive version, where we will be considering the arrival time. Now apart with the smallest burst time, we also consider when the process actually arrived to the system. Now let me explain this with the Gantt chart. Now you can take a notice here. The very first process I have is P1 and the arrival time is 0. That is on the 0th time, that is the only process in the system. So P1 has executed for 1 millisecond, after which there is another process, say process P2, that is arrived on the system. You can see there. Now what happens? So the preemptive version of shortest job first is what we are discussing. So now the process P1 shall be preempted and the CPU is taken over by process P2, because process P2 has a smaller burst time compared to your process P1. So we can notice that here. Now at the third interval of time, I have my process P3 that is arriving. Now again there is a comparison that happens with process P2 and P3. We can see the P3 is larger than P2, so there is no preemption that happens. So it is not going to preempt because P2 has a smaller burst time. So P2 shall continue for its next completion of the burst time. Eventually with your P4, Again, compared to your P2, compared to P4, P2 holds a smaller burst time, so P2 is allowed to complete it. Now that I have all the processes of the system that is already arrived by the 4th millisecond, so next I will be assigning the CPU to the process with the smallest burst time. Now the next process that I have with the smallest burst time is P4, and after that there is a comparison that happens with P3 and P1. Now the P1 compared to P3 and P1, again P1 has a smaller burst time compared to P3, so P3 shall be assigned the CPU. So eventually the Gantt chart is prepared in that way. Now calculating the waiting time is a little tricky when compared to your other scheduling process that we saw. Now what are the things that we need to consider when you're calculating your waiting time? There are two factors that you have to consider calculating your waiting time. One is the arrival time and the other one is your previous occurrence of the process. Now you can see here, now when I say process P1, the process P1 has waited for 10 milliseconds. I also, now from that 10 milliseconds, I am deducting the previous occurrence of process P1, that it has occurred for 1 millisecond. So that shall be deducted when I am calculating my waiting time. And with that I should also deduct the arrival time, because the arrival time is 0. I have just ignored it here. So it would be 10 minus 1 minus 0. So that is the standard thing that we do. And talking about P2, so P2 is waited for 1 millisecond minus the arrival time. So I would be deducting that arrival time. So P2's waiting is 0. The same for your P3 and P4. P3 has waited for 17 milliseconds and I would deduct the arrival, that is minus 2. There is no previous occurrences of P3, so I come up with the number 15. So P3's waiting time is 15. Talking about P4, P4 is waited for 5 milliseconds, and in that again I deduct the arrival, that is minus 3. I come up with the waiting time is 2 milliseconds. P4 also have not occurred previously in the system. If there is any previous occurrence and execution, those many milliseconds or burst time also needs to be deducted in the waiting time. So that is one thing that we need to consider here in your waiting time calculation. So calculating the average waiting time, summing up all that, I get 6.5 milliseconds. Turnaround time is no different. It is the same. It considers when the process is completed, irrespective how many times it has occurred previously. So the process P1 has completed at 17 milliseconds. Process P2 has completed at 5 milliseconds. Process P3 has completed at 26 and process P4 has completed at 10. So summating all that, I take the average and the average turnaround time would come up to 14.5 milliseconds. The next scheduling algorithm that we have is your round robin scheduling. This is another algorithm that is expected to be implemented as a part of your experiment. Now, talking about round robin scheduling, why was round robin scheduling introduced? To bring in fairness to all the process, so all the process get a fair chance to use the CPU. There were scheduling algorithms like priority scheduling, in which process with higher priority is always getting a chance to execute on the CPU, whereas the process with lower priority is continuously waiting to access the CPU. To resolve such a limitation, we came up with a round robin scheduling. So what happens in round robin scheduling algorithm? It is very similar to your first come first serve scheduling algorithm, but it is a preemptive version of your first come first serve scheduling algorithm. So what is the criteria for preemption? The criteria is the time quantum. What is the time quantum? The time quantum is a small unit of time or a small time slice that every process is given to execute. Once the time slice or the time quantum expires, the process shall be preempted and shall be given to another process in the queue. So let me just show you a snapshot of the process. Now I have process P1, P2, P3, and likewise I have its respective burst time. So how does the execution happens? For instance, if I say the time quantum is 1 millisecond, so process P1's burst time is 24 milliseconds. Out of that 24 milliseconds, only 1 millisecond shall be executed and 23 milliseconds is still remaining. But because the time quantum has expired, now the CPU shall be taken over by the next process, that is P2. P2 also executes for 1 millisecond and again the CPU is taken over by the process P3. Similarly, after P3, it goes back to P1. So that is why it is called as a round robin scheduling. So the execution pattern would be something like this: P1, P2, P3, P1, P2, P3. Again after P3 it is back to P1. So this continues until the process completes its burst time. So that is the concept of your round robin scheduling. Now we shall see how is the Gantt chart and average waiting time, turnaround time calculated. Now here I have taken, previously I spoke about time quantum now, just to illustrate how the round robin actually works. Here for my Gantt chart I have taken the time quantum to be 4. So each process gets a chance to execute for 4 milliseconds. So process P1 executes for 4 milliseconds and then it is preempted and the CPU is taken over by process P2. P2's burst time is smaller than the time quantum, so it completes the execution. Now why did I take such an example? There is one thing, students, you have to understand, that the time quantum shall not be reserved for the whole time. It shall execute only for its burst time. Here after P1, P2 shall not unnecessarily be reserved for 4 milliseconds or 4 time quantum. It will utilize only for its burst time. You can see here P1 has executed for 4 milliseconds, P2 is taken over, it is executed for 3 milliseconds and immediately after that P3 is taken over. You can see here 4 7, that is 3 milliseconds it is executed, and P3 takes over after the 7th millisecond. Do not be confused to allocate for time quantum unnecessarily. If P3 has a smaller burst time, it will execute only for its burst time. You can notice that here. And again after 7 it is 10. It is not 4, 8, 12. It is 4, 7, 10 because it is executing only until it completes its burst time. So P2 and P3 holds a smaller burst time than the time quantum. So we have P1 executing until it finishes its burst time in a span of 4 time quantums. P1 executes for the next time quantum and checks if there is any other process. Because there is no other process in the system, P1 would continue. That will happen every time the time quantum expires. So that is why we have shown P1 in the splits of 4. So 10, 14, 18. After 18 it again checks if there is any. No, again P1 takes. It checks there is no one else. P1 takes. So that is how it happens. This is how we will be representing the Gantt chart of your round robin. Now talking about the calculation of your waiting time and turnaround time. So how do you calculate the waiting time for your round robin scheduler? You need to consider the previous occurrences of the process in the system. Now process P1 has waited for 26 milliseconds, but process P1 has occurred 5 times previously in the system with the time quantum of execution of 4 milliseconds. That is why 26 minus 4 minus 4, I have done it 5 times to deduct that it has occurred previously for 4 milliseconds 5 times in the system. So how many ever milliseconds it has occurred and executed, that needs to be deducted when you're calculating your waiting time. So process P1's waiting time comes up to 6 milliseconds. I repeat, in the Gantt chart, process P1 has waited for 26 milliseconds, but I need to consider the previous occurrences of process P1. So deducting the previous occurrences of process P1, the waiting time of process P1 comes to 6 milliseconds, and process P2 and P3 is direct. Process P2 has waited for 4 milliseconds. Process P3 has waited for 7 milliseconds. So summating all that, I get the average waiting time as 5.66 milliseconds. The turnaround time is just as before. We take the completion of the process. So process P1 has completed at 30, process P2 has completed at 7, process P3 has completed at 10 milliseconds. So the average turnaround time is 15.5 milliseconds. To implement and execute. So what you are expected to implement has the experiment test. It is asking for 2 scheduling algorithm, that is your shortest remaining time and round robin. So what is the data structure, what is the considerations that you need to do for the board? So in your shortest remaining first, what is that you are expected to do? You are expected to calculate the average waiting time and the average turnaround time. So what is the data structure, what is the logic, or what is the calculations you are expected to do to design your program? So talking about the average waiting time calculation for your shortest remaining time first. First thing, you have to consider the number of process. the arrival time of each process and the burst time of the process. So what is the logic we have here? So whenever a process newly arrives on the system, you check with the process executing and you check with the process newly arrived. If the process newly arrived is smaller than the process that is executing, you preempt it and give it to the process that has newly arrived. If the process newly arrived is larger, has the larger burst time than the process that is executing, the process that is executing shall continue to execute. So you repeat this comparison of the smaller burst time with every process that is coming. And when you're calculating your average waiting time, as discussed earlier, you consider the previous execution and its arrival time. So that is how you will be designing your algorithm or the program for your experiment 7. I hope this will help you design and implement your experiment. And a quick recap of your round robin scheduling. So what are the things that you need to consider here? You need to consider the number of process, the burst time, and very importantly your time quantum. So here what is that you have to do when you are designing your algorithm? You have to check that the process expires at the time quantum and the next process takes it over, and this continues until the process completes its burst time. I cannot be exceeding for process, for instance for process P1, I cannot be extending my burst time more than or exceeding the burst time more than 24 is something that we have to take care of. We need to consider the number of process, the burst time of each, and the time quantum. So it goes in the circular fashion. It is going to repeat. It is going to repeat until it is completed its burst time. And as discussed earlier, so for the calculation of the waiting time, you consider the previous executions that it is completed. You deduct that or subtract that when you are calculating your waiting time. So I believe this will help you implement your experiment 7. Followed to this video, I shall also share some links that will help you build your program and execute your experiment number 7. I shall also discuss over your WhatsApp message or your mails what is the procedure, how do you execute, and how do you actually show me the results. I want all of you to execute your experiment number 7 and communicate the results to me. Thank you.